Welcome back. I hope you are able to print out this worksheet. If you are not, then please draw two big circles on your paper and follow along with us, because we're going to discover how to do arc length and area of a sector, finally getting to the point of the lesson. And in doing these two practice problems, I hope we'll make sense out of some of all those formulas that you just saw on the previous slide. So in the in the first problem, we are asked to draw the axes and label the quadrantal angles in degrees. So we have our x-axis, our y-axis, and I didn't leave much space here, sorry about that. So this is 0 degrees, or, if we go all the way around the circle, it is also 360 degrees. And in a positive direction, counterclockwise, 90, 180, keep rolling around, 270, and that does bring us back to 360. And then we're asked to draw a 90-degree angle in standard position. So standard position, it's going to have its vertex at the origin. This will be the initial ray, and we'll go to 90 degrees. I know you don't need anybody telling you how to do this. Okay, now the next question is crucial. This angle that we just drew here, and it includes its whole interior. What portion of the whole circle does this occupy? And I'm hoping, even though mine's a little lumpy looking here, that you'll notice that this angle takes up 1/4 of the whole circle. 1/4 or 25%. And the reason for that is because we took 90 degrees out of the whole 360, which does reduce down to 1/4. Next, we're asked to highlight the arc. I'm not sure this orange is going to show up any differently than that. It's not highlighting too well here. Excuse me. This is supposed to be bright blue. So this is the intercepted arc, S, for subtended arc. And also to lightly shade the enclosed area, which they call the area of a sector. A sector is just the same as a section. I didn't know if you've ever heard the military term, securing the sector. So I'm just going to lightly shade here the enclosed area. And it was key that this angle is 1/4 of the whole circle, or 90 degrees out of 360 on the whole circle. Since it occupies 1/4 of the whole circle, its arc length is going to be 1/4 of the way around the circle. Its area is going to be 1/4 of the area of the whole circle. And we're just going to use that kind of logic to solve these problems. So to find the arc length, it's going to be our fraction of the whole circumference. You have to remember the formula for circumference now. I also don't remember how to spell it. So our fraction is, I'm going to leave it as 90 over 360 for a moment, times the circumference is 2 pi r. So that's going to imply that the arc length is going to be 1/4 of 2 times pi times whatever the radius is. Didn't give it a radius. Let's see. A lot of you folks are turning 17, 18. We're going to make it 18 yards here. Instead of 18 years, we're going to make it 18 yards. And we just work that out. Now, pi, they don't want us rounding pi off. You could do things in your head like 2 times 18 is 36 and then cancel it with a 4. So if we take 2 times 18, 36, divided by 4, we'd have 9 times pi times square yards. They would like us to use the pi key. On the scientific calculators that we use here, I don't know if you can see this or not, the pi key is over on the left-hand side, right above the power key. On the graphing calculators that we use here, it's a little harder to find. The pi key is a second function key. I don't know if you can see it or not here. It's also over the power key. On the graphing calculator, the power's on the right, and it's a second function key there too. So let's try 9 times, where'd it go? Pi? Is that showing up at all there? Equals. And it gives us, we can round it off now if we want to. Round it off to maybe 28.27. Now, often on the SAT or on the AP exams, they'll allow us to leave our answers in terms of pi. There'll still be square yards, but they'll allow us to leave it. But we're just giving it a shot here, multiplying it out. Similar thing's going to happen when we find the area, and some books call this A. The book I'm used to using calls it K. I guess because it's the area of the sector. I don't know, but sector's not spelled with a K. This thing is not in focus. That's a little better. So the area of the enclosed sector here is also 1/4 of the whole circle. So it's going to be our fraction, which I'm going to once again write, because it's not always going to be a nice, neat 90, times, and you have to remember how to find the area of the whole circle. So that's going to be 1/4 of pi times the radius squared. The degrees canceled out, the 90 over 360, change it to 1/4. So this is going to be 1/4 of pi times 18 yards squared. So we could just go ahead and ask the calculator to take 1/4 times pi times 18 yards, but it's 18 times 18. You might want to put the 18 in there first and square it, then multiply it times pi, then divide it by 4. It's your choice. So just after pressing the magic keys, the calculator gave me an answer. We round it off. Going to round it off to the nearest hundredth this time. 254.47 square yards. Because when we take yards times yards, they come out to square yards. And if we're doing area, it should be in square units, but you knew that. So let's see if we can make some sense out of those formulas that were on the previous slide. If theta is given to us in degrees, then our angle is going to be some fraction out of 360. If it had been a 22-degree angle, it'd be 22 out of 360. If it had been a 200-degree angle, it would be 200 over 360. We're not going to do negative arc lengths, though. So the arc length which they call S for the subtended arc, is going to equal our fraction out of 360, whatever our angle is out of 360, times the whole circumference. And that's where they're getting that the arc length is going to equal the angle out of 360 times 2 times pi times the radius. Now they could say pi times the diameter, because that circumference is also pi times the diameter. They're just tending to keep it in terms of the radius. And then the area of the enclosed sector which some textbooks do call K, you may see it as A, is going to still be our fraction. I'm going to have to stretch this equal sign here. Of the area. The whole area. And the whole area of a circle is pi times the radius squared. So we're just going to take our fraction of pi times the radius squared. And that's it. That's the whole formula. So when we try doing this with radians, it's going to look a little messier in the beginning, but it will get simpler. Our angle is still a fraction of the whole circle, except we're not going to call the whole circle 360 degrees. In radians, the whole circle is 2 pi. So we're going to have the same kind of thing, except it's all going to be out of 2 pi. So the arc length and that's going to be theta, and I'm going to put a little r down here for that it's radians, out of 2 pi times the circumference, which I'm going to abbreviate. So we're going to get that the arc length equals our angle over 2 pi times circumference is 2 pi r. Well, this is going to tidy up nicely because the 2 pi's will cancel out. And we are left with that the arc length is going to equal our angle in radians. This doesn't work for degrees. Our angle in radians times the radius of the circle. You may remember a few minutes ago, we found the angle in radians, then an angle in radians equaled the arc length divided by the radius. This is the same formula that just multiplied both sides by r, by the radius. that tells us that the arc length is going to equal the angle in radians times the radius. The same formula, just solve for a different variable. Nice short formula. And same thing's going to happen with the area of the sector, which they call K. It's going to be our angle in radians out of 2 pi for the whole circle times the area of the whole circle. So that's going to imply that the area of our portion is going to equal this fraction times the area of a circle. The area of the whole circle is pi times the radius squared. Now the 2 doesn't cancel out this time, but the pi's will. So the area of the sector, they reduce it down. They make it our angle over 2 times the radius squared, because the pi's canceled out. Sometimes I'll say the angle times the radius squared, the whole thing divided by 2. And this is only if the angle is in radians. So we've got all 4 formulas that were on the previous slide, not as neatly, but all 4 formulas are included. But the slide left off a 5th formula. That's actually, forgive the word, a hybrid of these 2 formulas together. It takes out the angle. This 5th formula relates just the arc length and the area of the sector with each other. The angle isn't even the formula at all. So this 5th formula is going to relate the arc length and the area of the sector. No angle is going to be needed. And we're going to do it by combining. We're going to start with this one, this formula for area. We're going to rewrite it a little bit, make it 1/2 of the angle in radians times the radius, which is the same as what we have here. 1/2 times the angle times the radius squared. And then we're going to use a little crafty substitution. The arc length is the same as the angle in radians times the radius. And in the formula here for area, we've got the angle in radians times the radius. So we are going to substitute. We're going to take this and put it down. I'm going to make a mess out of all of this, I can tell. Put it down in here for this. So instead of 1/2 of the angle in radians times the radius times another radius, we're going to replace the angle in radians times the radius with just the arc length. So this becomes the area of the sector is going to equal 1/2 of the arc length times the radius. No angle in there anymore at all. A radius, an arc length, and the area of the sector. Of course, that means you have to know what the arc length is and you have to know what the area of the sector is, but just a different formula that works sometimes. If they give us the arc length and the radius, we don't have to figure what the angle is. We can do it with this formula. So let's try one more example here. Asked to find the arc length and the area of the sector once again. If the angle is 3, not 3 degrees, just 3, which means this must be 3 radians. Radians do not have any units of their own. I often write rads or radians just to remind myself that this is an angle. So we're asked to draw the axes and label the quadrantal angles in terms of pi. And Mrs. Milburn was very good about emphasizing how important it is that you know the quadrantal angle values because they give you your frame of reference for everything. So the initial ray here, 0 is still 0, whether we're talking degrees or radians or grads or whatever. This is still 0, but it doesn't get a little degree mark on it. And then going around the whole circle is 2 pi. So by the time we get halfway around the circle over here, that's just going to be pi. And up here at 90 degrees, which I'm sure you know by now, that's halfway between 0 and 1 pi. This is pi over 2, half a pi. And between 1 pi and 2 pi, they don't call it 1.5 pi, they call it 3 pi over 2. But it is 1.5 pi. Okay, and one of the last questions on the homework assignment from the first Nearpod, Mrs. Milburn asked you to also label these as the numeric value correct to the nearest hundredth. Now when we do the calculations, we don't round pi off to 3.14. We put it in the calculator using the pi key, the whole value. But just to get a frame of reference, pi is 3.14, March 14th, Pi Day. So then 2 pi should be twice as much. So this should be about 6.28 radians all the way around the circle is only about 6.25 radians. If a whole pi is 3.14, then a half a pi should be half as much, which is about 1.57 radians. And then 1.5 pi's should be as much as 1 pi plus half a pi, which is about 4.71 radians. It'll make things faster if you memorize this, but if you know what pi is, it's not that hard to figure out what the rest of the rounded off values are on the quadrants. So when they say that this angle is 3, well, 0, 1.57, 3.14, that means it's probably going to be really close to here. So our initial ray and our terminal ray, which is getting kind of quavery here, we expect it to be something like that. It's going to be really close to halfway around the circle. Because these radians are big, chunky angles. So the question, which was at the top of the problem this time, is to find the arc length and the area of the sector. So the arc length is going to be our fraction of the whole circle. Well, our fraction is an angle of 3 out of the whole circle is 2 pi. We're not using the 6.28. That was just to get our bearings as to where to draw the angle. So our fraction of the whole circle is 3 over 2 pi times the circumference. So that's going to be 3 over 2 pi times the circumference is 2 pi r, which just comes out to our angle times the radius. And when you work with radians a lot, you will skip over this hour fraction of the whole circumference and just go that the arc length equals the angle times the radius. So for this particular problem, I forgot to say what the radius is. Well, how about we just stick with 18 yards? It worked last time. So in this case, the arc length is going to be 3 times 18 yards. So the arc length is going to be 54 yards. The angle in radians doesn't have any units, but the arc length still does. The arc length going around this way, all the way around to here. And the area of the sector we can do it as our fraction of the whole 2 pi. If you don't want to memorize another formula here for area of a sector. So we could take our fraction times the entire area of the circle, and then just simplify it. The pi's will cancel out, and we'll have 3 over 2 times the radius squared, which is what the formula comes out to. But if you don't want to memorize it, just take our fraction of the area, our fraction of the area. So for this particular problem, we'd have like 1.5 times 18 yards again squared. So according to the calculator, this is something like 486 square yards. So this was quite a long video, and I'm sorry to have kept you, but it was necessary, I thought, to go through these examples. The assignment will be a review for the types of problems that we've done in the last 2 weeks. And you should do the review before you take the quiz. And the answers to the review problems will be posted so that you can check your work. If you have questions, as always, please contact one of us, and we'll be glad to help.